Okay, a couple more examples here of calculating various information related to weak acids and weak bases. So the first problem here, we want to calculate the pH of a 0.2 molar solution of HCN. That would be hydrocyanic acid. We're given the Ka. It's 4 times 10 to the minus 10th. So again, we could use HA. HCN is fairly easy to write. Let me just use HCN in this case. It's an acid, so it's going to react with water, and it's going to protonate the water. So that's going to make hydronium ion, and that's going to leave the conjugate base, which in this case would be cyanide ion, as an aqueous solution. Now, this is an equilibrium, so we'd want an ice chart. All we really know here, other than Ka, is the initial concentration is 0.2 molar. Now, we know there's no products, as we have not yet approached equilibrium under initial conditions. So we know the equilibrium is going to shift forward, minus x here, plus x here, plus x here. That means at equilibrium, that would go as x, x, and 0.20 minus x. Now, if we just plug this in to the Ka equation, put that down here, Ka would be the products. So that would be hydronium and cyanide over the reactants, which would be HCN. And if we just plug this in, excuse me, this would be x squared over 0.20 minus x. Now, you may recognize this would lead to an equation we would need to use the quadratic formula to solve. Now, it turns out, specifically with acids and bases, this is often going to be the case, but just because of the range of equilibrium constants we have for acids and bases, often the equilibrium constant is small enough that we can ignore this change. Excuse me. The measure I like to use to decide whether it's mathematically okay to forget about the change here is to look at the ratio of the concentration that you're starting with. So I'm going to take the concentration of my weak acid in this case, and I'm going to compare that to the equilibrium constant for the weak acid. Now, we mentioned before, if the equilibrium constant is very small, that means it's a reactant favored equilibrium. There's a much higher concentration of reactants than products. So if you have a relatively high concentration of your weak acid with a relatively small equilibrium constant, that means this x is going to be really small. So the measure that I like to use is to look at this ratio and see if this ratio is 1,000 or higher. If it's higher than 1,000, then we can generally ignore this x, and it's not going to change the value we would calculate for the concentration of weak acid, and it's not going to change what we would calculate for the pH. So we're looking for that to be greater than 1,000. Now, in this particular case, this would be 0.2 divided by 4 times 10 to the minus 10th, and that is 5 times 10 to the 8th, right? Which is a lot bigger than 1,000. So that means this x here is going to be really tiny compared to 0.2, and that means we can simplify this problem by removing that term, that minus x term, from our Ka expression. And whenever we can do that, it's really going to simplify what's going on. Now, you do have to be careful. If you can't do that, you will have to go back and do the quadratic equation, which we will see from time to time that we do need to do that. But now we can just take our Ka, multiply by 0.2, and then take the square root to solve for x. Okay, so 4, calculator turned off again, 4 times 10 to the negative 10th times 0.2, and then take the square root of that answer, and we get x here is 8.9 times 10 to the minus 6th, right? And x here is hydronium ion concentration, so that would be a molarity, right? And what we're asked here is to calculate the pH, so we really want to turn this into a pH, so the pH would be the negative log of that value. Just do that. That's already in the calculator. Negative log of that previous answer would be 5.05. Right? And you can actually see that the assumption is pretty good here. If we take 0.2 and subtract 8.9 times 10 to the minus sixth, and it's a two significant figure value, it's still going to round to 0.20 when we go to calculate what the concentration of HN is at equilibrium. So really good assumption in this case. We'll see some other cases where we're getting close to the point where that assumption might not be valid, like the next example. Now, the next example, this is a problem that is a little trickier to interpret because you've got to be on the lookout for the presence of your acid or base. Acid's generally pretty easy to recognize. You've got the H in your formula, or you've got acid in the name, right? But bases with a negative charge can kind of be part of a salt that we really don't notice unless we're paying careful attention. So we want to figure out the pH of a 0.25 molar solution of sodium carbonate. Now, when sodium carbonate is dissolved in water, it's going to separate into its constituent ions because we know sodium salts are always soluble. We should also recognize sodium is not going to have any effect on the pH because it's the conjugate of a strong base. It's the conjugate of sodium hydroxide. So what we're really interested here in is what is carbonate going to do in this aqueous solution? Well, you may recognize that carbonate, there'd be lone pairs on the oxygens. It can act as a base. It would react with water and do what bases do, which is grab onto a proton. That would make hydrogen carbonate in solution. That would be the conjugate acid form, and hydroxide ions in solution. Right? Now, we can do an ice chart for this reaction as well. If our solution was 0.25 in sodium carbonate, it's 0.25 molar in carbonate as well, although you do have to watch for stoichiometry there. If there's maybe two equivalents of your base in the formula for a salt, you'll have to factor that in. 0, 0. Right, so again here, minus x, plus x, plus x, 0.25 minus x, x, and x. Now, we also want to see if we can make our assumption here. So if I take the concentration of my base, so concentration of carbonate, and I divide it by the Kb that I'm looking at here, that would be 0.25 divided by 1.8 times 10 to the minus fourth. And again, what I'm looking for is that greater than 1,000? And in this case, it is 1389, but it's just barely greater than 1,000. So we'll see here as we work this problem that, yeah, we're actually getting to the point where this x is meaningful in terms of how does it change this concentration, right? But we can still make the assumption here. So plugging into the Kb expression, that again is going to be products over reactants. Both of my products are x. My reactant, I can ignore the minus x, is just 0.25. We're given that Kb is 1.8 times 10 to the minus fourth. Right, so again, we can solve for x in a pretty straightforward algebraic sense here. So 1.8 times 10 to the minus fourth, multiply through by 0.25, and then take the square root of that answer. And x here would be 6.7 times 10 to the minus third. That again would be a molarity since we're solving for the concentrations of our components. In this case, it's not hydronium though, it's hydroxide. Now that puts us one additional step away from calculating the pH. So we could use the hydroxide ion concentration to calculate the hydronium ion concentration using hydroxide ion times hydronium ion equals Kw. But there's another version of that equation that's a little more helpful here. So hydroxide ion times hydronium ion is equal to Kw. Well, if you take the negative log of all of those pieces, the negative log of hydroxide ion concentration is a quantity called POH, so related to pH, but based on hydronium, not hydronium, on hydroxide. Negative log of hydronium we know is pH, right? And the negative log of 1 times 10 to the minus 14th is 14. So the pH added to the POH is equal to 14. So what we can do in a problem like this where we calculate hydroxide is first calculate the POH, which would be negative log of that previous answer. And then we can just subtract that from 14. And that's a little easier than having to go through the exponents of using Kw. in your problem. So pOH here would be 2.18. So that means the pH would be 14 minus 2.18 would be 11.82 for this particular problem. Okay, real quick, the last bit at the bottom here. Acids can get quite a bit more complicated. So there are what are referred to as polyprotic acids. A polyprotic acid has more than one proton in its structure that can be acidic. A good example here is phosphoric acid. You start with H3PO4. There's actually 3 different steps where phosphoric acid can act as an acid until you finally get to the phosphate ion. But what's important to recognize here is taking H plus away from a species that is getting more and more negative becomes harder and harder. So there's actually a pretty big gap in terms of the value of the equilibrium constants here. So we're at 10 to the minus 3 for the first acidic proton, 10 to the minus 8th for the second, 10 to the minus 13th for the third. So the result is, if we're looking to determine, say, the pH of a solution of phosphoric acid, right, the amount of H plus, which we would think of as H3O plus generally when we include water in the equilibrium, produced according to this equilibrium is going to be 5 orders of magnitude less than what we have here based on the values of Ka. So we only ever need to consider the first equilibrium constant here. So we would calculate how much H plus you get here. The contribution from these would be small. If we're going in the opposite direction and we start with phosphate, right, we'd only need to calculate the Kb of the first backward reaction to calculate the pH of that solution. So a polyprotic acid can look a lot more complicated, but if we look at the values of the equilibrium constants, generally it's going to be about the same level of difficulty of a problem.